that presentation. You might not find too much news, but I'd be excited to talk a bit more after and take questions and hear you guys' input.
So I think we have an exam on Monday, don't we?
We do, yes. It's not that presentation. I have that in the background, but I think that would be a bit too long. I don't want to completely spoil everything, although most of it is not.
Well,
right.
we ought to invite everybody to Lukas's defense on Monday.
It's going to get a bit packed in there, I think, or
we may have to have a bigger room.
Yeah.
Yep.
I haven't organized a bigger one, maybe on purpose.
Yeah.
All right. I'll just get started, and I'm trying. I don't think I can see questions on the side, so probably best to just wait until the end or yell at me, then I can stop. But yeah, first of all, I'm excited to talk to you today and introduce you to what I've been working on pretty much for the last almost 4 years. Yeah, it's some pretty interesting work. And also, if you're in the field and you're potentially looking for some research avenues and you're looking for a topic, I think this could be a really interesting piece of work to continue. And there might be possibilities for someone to actually take over and build on top of what we've done over the last couple of years. And I think it's really cool work, but I'm also a bit biased. So what I'm going to talk about today is basically expanding a framework that we built that is used for using mobile lidar data for underground geotechnical monitoring, and expanding on that framework by enhancing voxels. And I will get into what that specifically means. Second. So here's a quick agenda. I'm quickly going to go over what mobile laser scanning actually is. For those of you who haven't heard that term before, I'm then going to showcase some applications that it is used for currently, and some of the limitations that come with it. And then I'm going to dive a bit deeper into my work and what I've been doing and what we've been working on in terms of this framework and how we utilize geotechnical data such as geology modeling and microseismic data to basically supplement mobile laser scanning data. And then at the end, I'm just going to touch on some future potential for that. And like I said, if someone is interested and looking for an area of research, that is probably a cool place to listen to. So really briefly, what laser scanning or mobile laser scanning is some of you might be familiar with static lidar scanning, which is used for many geological, geotechnical applications underground, but also in surface mining operations to collect three-dimensional data of geometry. For underground mines, it can be very useful as mobile laser scanning, as the name implies, doesn't require specific scan stations. So the system, you can see an example of that here in the left of the screen, is fairly small and can be moved while it's collecting data. The main benefit of that is that it is much faster than static laser scanning. So you basically take your system, you turn it on, and then you can create a map of 3D points, as you can see here on the right of the screen, where you can cover very large areas, 2.5, 3, 4 kilometers in a fairly short amount of time. This particular scan here on the right took about 45 minutes. That was for like 2 passes going around. It was about 2.5 kilometers long. So you're able to collect a lot of data really quickly and do that over multiple epochs. So basically, you do that in a time series manner and collect multiple scans on different days. And then you can overlay those scans and basically observe geometric changes in the point clouds. And obviously, that is very interesting for geotechnical monitoring, for rock mass deformation monitoring, to detect convergence. We've also done some tests on rockfall detection. So a lot of applications in that space. So here are some of the other applications. Quite a few of them are actually pretty common already in underground mining environments. One of the I would say probably the most common is as-built generation, which is commonly used for underbreak or overbreak analysis. So basically you take two separate scans before drilling and after drilling and blasting, and then you can compare those scans and see what your actual blast geometry looks like and where you might have had under or overbreak. And then you're also able to correlate that with geology data, for example. You can pull in a geological model and maybe see if there's any correlation. Then I already mentioned the time series monitoring, and that is really interesting. For example, in a block cave mining operation where you have panel convergence, and you want to make sure that your excavation remains stable and that you're aware of any changes that are happening. Another interesting use case is hazardous area inspection. So, for example, if you're in an underground mine that is prone to rock burst, that could be an interesting scenario. After you had a seismic event, you can send a system on a robotic platform, collect spatial data of the actual excavation and see what happened. And that kind of alludes to a point, like what a lot of people might be more familiar with this in terms of mobile lidar scanning is the use of these systems on drones. So for example, for stope mapping, that is a very common practice nowadays in many underground mines. So able to put the system on a drone, fly the drone into a stope, and then collect very rich data sets of that stope. Phase mapping is another example that is potentially interesting. There are some limitations with some of these systems, as the noise, the sharpness of the point clouds is not as high as that is of static lidar scanning systems. So just for visual inspections, there are some limitations around that. But the field is rapidly advancing, and I think even in the time I've been working on this, there have been some pretty impressive advances in terms of the sensor technology that is used in these systems. Here are some examples of the first study we did that was published last year. And we basically utilized a mobile lidar scanning system to see if it is able to pick up small as they might occur during a rockfall event in an underground mine. You can see some examples of that on the left, and you can see the rock number 6 there, barely spottable in the picture, is about 2.5–3 centimeters in size, and we're able to pick that up. We're able to pick that up quite well in the actual scan. And then larger rocks are really well distinguishable in the scan if you overlay multiple epochs. Here's an example on the right of using this technology on a mine panel for convergence monitoring. And if you look at some of the cross sections here, you can see that you not only pick up convergence, as in this example below here, but also infrastructure work. In this case, they poured the floor in between the scans, and these really nicely, which also kind of alludes to one of the issues with this technology is that, let's go back here. You can imagine this is a fairly large area, as I said before, like 2.5 kilometers. If you do these scans regularly and you have to go in and manually look at those point clouds and try and figure out what has changed, what are the relevant changes, that can become quite cumbersome and time consuming. So the sheer amount of data that is collectible by these systems can actually pose quite a challenge for the utilization of this data. Yeah, and here are some other limitations within this space. I've already mentioned the first one, time and experience. So it takes quite a bit of time to analyze the data, and then you also need to have some workflows in place, and you need to know how to actually do this to generate reliable results. Then, like I said, the quality and repeatability of these results is sometimes a challenge if this is something people haven't done before and don't have a lot of experience with. So it definitely takes a bit of practice, and if you can establish a workflow and an SOP, that I've seen that being very effective in actually getting the most out of this data. And then I think at the moment a key limitation still is the lack of automation. So there's trials where these systems are put onto drones that are flying autonomously. There's trials where they are put on robotic platforms, such as the Spot robotic dog, if you've seen that, to do those inspections automated in an automated fashion, but that's still fairly early on at the moment. So let me now go a bit more into my recent research, which really focused more on the data analysis part to do change detection on these large data sets and do that efficiently and reliable, and like I said, in a more automated fashion. And what we did is we developed a framework that is based on an octree, and I'm going to talk on the next slide a bit more about what that is. And basically what it enables us to do is do faster change detection, so it's very efficient. It was originally the original concept of octrees, or in this form, using octrees was quite frequently in this still used for robotic mapping. So autonomous platforms that have to process data on the go as they're mapping. So it's very efficient. We also did some supplementations to this framework to make it more reliable and accurate and produce fairly decent change detection results. And then lastly, we also showcased that this can be used to automate the data processing in quite interesting ways. And like I said, this framework approach is really quite interesting because you can build on it, you can think about potential applications and expand on it, and makes it a really cool research platform. On the other side, it's also interesting for potential industry applications, as it can really be tailored for a specific use case that a mine site or a technology vendor might have. Here's a very big picture overview of what this actually looks like. So on the left, to just give you an idea what an octree is, if you haven't heard of that before, it's basically a three-dimensional subdivision of space that enables very fast search and query operations within the data. And what we then do is on the lowest level of the octree, where we have a voxel that contains points from a mobile lidar scan. We take those points, and then we basically compute summary statistics of these points that are contained in the voxel and represent those as a covariate. If we represent those, they're basically an ellipse within the voxel, which gives us a bit of a better understanding of the actual geometry that's contained in the voxel and how the points are distributed within the voxel. And the main benefit of that really is that it balances the information contained in each voxel with the need to actually store a lot of data. Because again, as I said before, these point clouds can become really large. There's a lot of data generated with it, and trying to find ways to actually compress that data and reduce it while maintaining information is quite important. On the right is an overview of the framework that we built. It's primarily, at this point, it's 4 steps. So we basically take in multiple point clouds. Here's 2 different epochs of point clouds. We then feed them into the octree, compute those summary statistics for each voxel, and then on the same side, we also can now take in geological and seismic modeling data. These then go into their separate octrees. In this part here, what I called here the geotechnical module, we can perform some computations and computational operations with this data that we are interested in, and we then feed that back into the change detection octree. So in the second step, once we have the mobile data into our framework, we can perform the change detection using an adapted chi-squared test that results then in candidates change candidates. So basically voxel that have a very high probability that they changed between 2 different scan epochs. And once we have those change candidates and integrate them into another octree, we can then augment this octree with the geological and seismic data. So basically we end up with a very compact form with a lot of data condensed into interesting regions, those that have changed. And we can then do other computations with these. In this example, we're doing a RANSAC algorithm, which is basically a plane. In our case, it's a plane fitting algorithm where we detect the floor of the mine drift, because that often has changes in it that are not relevant in a geotechnical sense. There are, of course, exceptions where you actually have floor heave and things that are actually relevant, but oftentimes you have equipment moving, losing material, and those are all changes in the mine drift that are not necessarily related to geotechnical. Then lastly, what we can do is a clustering algorithm. That is the dbScan part here, which basically takes voxels or regions of voxels, looks for highly dense regions of voxels that have changed, and then groups them together, labels them with a label to basically end up with specific clusters that are potentially spatially correlated to changes. And then once we have all this data, we can take that out and do a geotechnical analysis on that. And I'm going to show you some results or some examples of what we can do with that. Okay. So I already kind of mentioned this, the concept of these enhanced voxels is basically supplementing these change detection voxels with more potentially geotechnically relevant data and using multiple sources of data to supplement our mobile laser scanning data. This could also be expanded into other data forms. I'm going to touch on that in the end. And the key idea behind here is we saw in our previous paper, and if you're interested, I can send you a link for that. I think I have it at the end of the presentation. We saw that the performance is really just quite significantly better than what other change detection algorithms offer at the moment. So we might as well use all of that performance overhead that we have to actually do some more computation on top of that. Here are some really simple examples of what this can then look like. Looking at the left, this here is data from a mine that we got. We have two different scans and two different levels that are not connected, so fairly small scan regions here at this point. And then we have a fault model. We cut that down to the region of interest here with those two scan areas. And then we can basically take this fault model, also voxelize that. In this case, you just see the actual surface model. And then correlate the voxels of the fault model with the voxels. That's what you basically see here is the smallest unit within this octree, a voxel that has mobile lidar scanning data within it. And then we can do a simple distance computation. So we can basically tell that a voxel that our lidar data point that was collected in this region here, for example, has a very short distance to the next closest fault, and then to the next closest fault intersection, I should say. And then other parts of the scan, for example, up here, have a much longer distance to the next fault intersection. And that could potentially be interesting because there's quite a bit of research out there and experience in underground geotechnical underground mines that suggests that there is a correlation between the distance of a drift the distance of an intersection, or the distance from an intersection of a fault with a drift and geotechnical changes. So that was kind of the hypothesis that we were investigating. We see here on the left one of the scans. We see that here from the top view and the bottom view. So this is the floor of the mine drift. And then we basically just did some simple statistics and printed some box plots and saw if there's actually a significant difference between the changed voxels and the non-changed voxels. And what you can see here in this data set, these box plots here refer to the whole scan area, and they showed three different distance metrics. So we can not only do a singular one, which in this case for the A is the Euclidean distance to intersections. We can do a connected path distance, so basically stringing together multiple voxels to find a connected path, or to do a distance to any fault within the model. And as we can clearly see here in these box plots, that we have a pretty high standard deviation, but we can also see a trend towards changed voxels. So the red box plots here showing a lower mean distance to the fault intersections. You can see that through all the different metrics. And what's also kind of interesting is, as you can already pick up here in the image, in this fault damage zone where you have some pretty significant changes. In this case, the changes in the floor are very likely actually related to the fault. You can see that this difference between the two voxel classes, so the unchanged and the changed voxels, is actually significantly larger than for the whole data set. And there's some other things that we can do, and I'm already 20 minutes in, so I might want to shorten this up a little bit. But one other example that we looked into was seismic attenuation modeling. So basically using microseismic monitoring data, storing that into our voxels, and then trying to estimate the seismic energy exposure that each mobile lidar data voxel would receive. So here we have a mobile lidar data voxel with points within it. We have a fault model that's symbolized by this purple fault, or by those purple voxels here. And then we have seismic events that happened. What we do is we calculate the combined seismic energy within each of these voxels. And then we use a ray casting approach, basically casting a ray from each seismic voxel to a mobile lidar scanning voxel. And if this ray intersects a fault, we can then change the attenuation model. If it doesn't intersect, we just use a simple geometric attenuation, basically over distance, the seismic energy is decreasing. If a fault intersects in our test, we assume that we would have increased scattering fault region, and therefore modify the function to decrease the energy even further as it gets translated into the mobile lidar voxel. And then we basically end up just summarizing or summing all of the energy for each individual voxel. And what that then looks like is something like this. Here's a simple example where we simulated an event. You can see here is pretty clear. So this is the seismic energy in Joule. Again, this is more of observing relative trends rather than the actual seismic energy. It's definitely some work required to dial that in more and calibrate the actual seismic attenuation functions. But what you can see here is in a simple case where you just have geometric attenuation over distance, you see a gradual fall off of the seismic energy exposure. And then if you actually consider the faults to be increasing the scattering and thereby the attenuation of seismic waves, you see this more abrupt cutoff in seismic energy exposure after each seismic ray intersects one of these faults. And here's a larger scale example. This is actually an earlier impression how that would look like on a larger mine scale. You have some stopes here on the right of the scan, and then all those points here represent seismic events of various magnitudes. We actually don't use the magnitude at the moment, but actually seismic energy released by each event. And then we try to approximate the exposure. And as you can see here, the closer you are to high magnitude events, these tend to have a fairly big impact on the actual accumulated energy within each of those lidar voxels. You can see here, the darker the color is, the more seismic energy exposure we expect. This is in a paper under preparation. We actually showed that in the data set that we have, that this seismic energy actually correlates quite well with the changes, and not only with the change in the unchanged and changed voxels. So changed voxels generally tend to receive more seismic energy in this data set, but it also correlates with the changed magnitudes. So with the actual centimeters of change that occurred or were measured within the voxels. Then lastly, just to wrap up here, one of the other use cases that we tested was this combined RANSAC DB scan segmentation and clustering I spoke earlier to. And just need to yelling into my my microphone here. And what you can see here is basically, again, the change detection results colored by the magnitude of change. Resulting from this should actually be a chi-square test, not a t-test, from our chi-square test. And then we utilize the ransack algorithm to segment out the floor. You can see that here quite nicely how the floor is colored in gray. We have some areas here that weren't classified correctly because of the some unevenness in the floor. At the moment, we just use a single plane fit for the whole drift, which has some limitations to it. And then other areas that actually didn't have any lidar points in it. So there's some blank spots in this region here. What you can also see is after the dbScan clustering algorithm, you end up with these regions here that have fairly high concentrations of change. We filtered out all the filtered all changes that are lower than 2.5 centimeters before and then clustered them. And if you do that, you can see that these change regions here correlate to these areas on the left. And you can see that they correlate quite nicely with the intersection of the fault here. And yeah, that's pretty much it. Some ideas for future work and maybe some limitations of the study thus far. I think what would be really interesting to do is to test this with larger data sets. Like I showed before, these data sets are fairly small, a couple tenths of meters. What we really designed this approach to and showed that it is working on is really large data sets of kilometer type size whole mine panel. So I think that would be really cool to do that. And I think the actual significance or relevance of the statistical analysis would be much more, or would be improved using actually higher quality and larger data sets. That's another limitation of the data that we had. This a fairly old system. There's already systems out there that collect data at a higher resolution. Also better actually lidar accuracy. So that could be interesting. Do a comparison study of how do those systems actually compare and what is the outcome, statistically speaking, of these results. Then also really interesting, I think, is using data with a higher temporal resolution. So doing more frequent scans. Some of the data sets that I showed you were 4 years apart. So that's a massive time frame, obviously. So others that we tested were about 4 months apart. I think what would be really cool to do is to actually have data sets that are collected on a weekly, maybe even daily basis. Fairly uncommon to do these scans on a daily basis. I'm not aware of many mines that do something like that. To investigate, and I think that's where really the value of our approach comes in, having much bigger data sets. And then I already mentioned on that improving the seismic modeling is really just a proof of concept for the most part, showing that we can actually do these types of calculations within our framework, and we don't need to use other software for that. But there's certainly room for improvement in that space. And then also other data types. There's a host of other in situ instruments that are used for geotechnical monitoring, and all of these could potentially be integrated in our framework. And actually, most of these should be fairly easily integratable compared to lidar data, which definitely has its own challenges. And then also, I think doing more sophisticated statistical analysis, potentially building more complex machine learning models on top of this that are able to capture nonlinear trends in the data. I think that could be hugely interesting and important, especially talking about these big data sets. Yeah, that's pretty much it. Here's the team or my committee that has helped me tremendously on this work, and I've received support from various institutions, and especially the industry collaborators we had are amazing. Kid Creek has been super helpful with their data. Emerson is one of the companies that built some of the most cutting-edge mobile lidar scanning systems. Mind Vision Systems just released a really cool tool for face mapping. So they've all been involved in this in one form or another, and super grateful for their help. And it's been a great project. And I would be curious to take any questions if you have anything that you're interested in, something I didn't explain in enough detail, or something that was a bit hard to follow. Please let me know.
So yay!
Thank God you're saying something. Otherwise it would be silent.
So Lucas, I really see, a very interesting applications, particularly when you're getting significant displacements that are of great concern. And this fits into when you're dealing with underground into swelling or squeezing situations where overstress is occurring, right? And using the ground reaction curve kind of comment, the idea of being able to get verification very quickly or validation of a model would be very interesting. And that fits into the kind of construction, are you familiar with it, called sequential excavation method, the NATM?
Mhm.
Have you heard of anyone incorporating, because that's a displacement-based method. That's the whole heart and soul of it. Is anybody in the tunneling industry using this kind of technology? Do you know?
First of all, I have actually, like, going over my dissertation, I mentioned the NATM pretty early on, I think, but I honestly haven't really looked much into it after. In terms of scanning in tunneling environments, there's definitely been applications before mining even that use primarily static scanning, and that also couldn't tell you the name of the author of the paper, but I'm pretty sure I've read a paper where they used the NATM in conjunction with deformations from lidar scan. I think it was static lidar scanning at that point. I think tunneling environment, I'm not sure if mobile scanning, if you're talking about construction of a tunnel. If you're talking about maintenance, then that's maybe something else, but NATM is mainly during construction, right? So I'm not sure if mobile laser scanning would be the most appropriate tool, because you potentially would be able to just put a more accurate resolution static scanner and get better accuracy data. Yeah,
it could, but sometimes you're not so much interested in a point measurement, you're interested in a trend. Are the displacements accelerating? And you want it fast, and you may not know exactly where you want it. So the idea of being able to do something, anyway, it's something to think about.
Yeah, no, definitely something I'm going to write down here, because maybe this might be a question that comes up later.
It might.
Yeah, no, I think that's definitely, like, in a tunneling space. I tried to publish the first 2 papers in tunneling journals. I think my work was more focused on the underground mining community, especially with those detecting changes such as rockfall. I think that's something I haven't really seen a lot. I'm not sure if this might be not really too much direct value in it. That's why it's maybe not super interesting. But I think, like, the rockfall, like monitoring discrete, like if you have spalling of shotcrete, or rockfall where you don't have shotcrete, building a trend of, like, maybe you're not interested in the 2-centimeter rock that fell down, but you might be interested in trends, like you said. Over time, if you see an increase in small rock falls, you can build a distribution of the sizes of those over the whole mine, and you basically end up with a heat map of where you have a lot of those small rock falls. I think that could be really interesting. I'm not sure if that's the tunneling industry is really interested in these applications.
Well, I mean, it depends on whether you're talking about the tunneling industry, like if you're tunneling for hydro development in the Himalayas, where you have fairly rapid squeeze, and I mean, you may, the whole game is to try to put in enough support to slow the rate of squeeze, right? And you need to know fast. So it's interesting. Yeah. So combining this with, like, AI and maybe putting it on a robot and let the robot go into more dangerous places and make measurements to try to figure out what's going on.
Yeah, no, absolutely. I think you're definitely hitting a point there with a time series and rapid, a lot of data, kind of what I was alluding to at the end.
Yeah.
I've been mainly looking at 2 really discrete scans. If you actually have daily scans, maybe even twice a day, you have so much data that you can use and average out, and potentially actually basically compress those points to tell you more than you would be able to see if you have a 4-month in between. I think there's a lot of really cool work that could be done in the space if you have these data sets collected regularly.
Yeah. Well, good. Well, thank you very much.
Yeah, thank you, Priscilla. Looking forward to seeing you. Is there any other questions? Was there something in the chat, or I don't see anything? There's no other questions. Always happy to get in touch. Feel free to reach out over email or LinkedIn.
Okay, there is no question in the chat part. So okay. There's no question. So if no one else has a question, I guess. Thank you, Lucas, for your presentation. That was amazing. I personally enjoyed it a lot, and you did a fantastic job. Thank you very much. Just a couple of announcements for next week. We are having a presentation from USGS. As again, it's going to be on Zoom, and for the next semester, the seminar committee, the seminar coordinator people are going to mostly graduated. So if anyone interested, please send an email to me or Sarah. And thank you very much.
Thanks for having me. Bye-bye.